Okay, this is our last video for our content for equilibrium, and then there will be 3 videos coming up on some AP questions that I think will help you out right before the test. So you'll be required to watch those right before your test. Now, what we want to look at now is mathematically the relationship between temperature and an equilibrium constant. We've talked about it conceptually, qualitatively quite a bit. Now we want to look at mathematically. This is the second of the 3 equations that we will see of this form. So there's a total of 3, and this is the second one we've seen. The first one related the rate constants, K2 over K1, and if you remember, that was equal to minus E sub A over R times, if you keep that negative sign there, 2 on top, the 2 first, these will all be in the same form. Books don't do that, but I'm going to try to make that consistent for you. You will see this in college chemistry. You'll see this maybe in engineering classes. It's a very important concept. The Van 't Hoff equation mathematically is not covered on an AP test, but I think it's a really helpful way to understand the underlying concepts behind what's going on. Now, much like what we saw before, if we want to label the graph, we're going to put the natural log of K as our Y, right? Because that's in that form, and 1 over temperature would be our x-axis. Now, in this case, we always had a negative slope. So the negative slope, accounting for that negative, always gave us a positive activation energy. In this case, it's possible for delta H to be either negative or positive, endothermic or exothermic. So let's take a look at our 2 possibilities of lines. Let's first deal with that which has a positive slope. So if I have a positive slope, that positive slope is equal to the minus delta H over R. Remember, that was the slope in this. So that's equal to minus, let me get a better color, see if I can give you a better color here, minus delta H over R. I'll talk about units in a minute. Okay, so if we have a positive slope and a negative here, that means delta H is going to end up being negative, which means we're talking about an exothermic reaction here. Okay, so that's one way to look at it. Let's take a look at the other possibility. What if we have a negative slope when we graph natural log of K versus 1 over T? Well, if we have a negative slope, and that slope is equal to a negative delta H over R. R is always positive, remember. Those 2 negatives will cancel. That means delta H is going to be positive, which means that would be an endothermic reaction with the negative slope. So we'll see both here. With this one, it was always the negative slope. Now, let's take a look at this mathematically. But before we do, I want to use LeChatelier's principle so we can predict to see what whether or not our final mathematical answer is logical. Boy, that's a wonderful technique to be able to do. And it's really what we as chemists are hoping for from you, is that you won't just plug blindly into an equation, but that you'll think about it logically as well. Now, since delta H is negative, that means it is exothermic. So that means that heat is a product given off here. Now, we are going from 25 degrees to 0 degrees Celsius. So we're decreasing our temperature. So if we're decreasing the amount of heat, we're removing the product, so we have to replace the product. So that means we're going to increase our concentration of our product, N2O4. Now, since that is in the numerator, that means that we're going to have an increase in Q. All right, and when it reestablishes equilibrium, we're going to have a new K that's greater than our old K. So we expect our new value of K to be bigger than 8.8. That's the take home from there. So let me get myself some workspace on here. Oh man. Okay, let me get some workspace on this, and we will continue with our video. All right, so we have here our formula, so let's plug into that. We have the natural log of K2, that's our unknown, over K1. Now, minus, let's deal with the R first. R, because there's an energy term, has to be 8.314. Now, 8.314 is in terms of joules per mole Kelvin. So that means we have to have our energy term in joules. So we need to write that energy term as minus 57,200 joules. And it means that our temperature has to be in Kelvin, which as soon as you put in 1 over 0, I hope you would realize that that is an undefined number, and we don't like those. So minus 1 over 298. Now, if you do this algebra, this mathematics, I get K2 is equal to 73, which was indeed exactly what we expected. Okay, we're going to be working on this in class, so until then, this is signing off.